And of course, the ability to perform a well-defined task. If there is a drone swarm for the defense, it can work in that area. If the drone swarm is for the search and rescue mission, it can work for that area. It depends upon the area. Classification of drone swarm, actually based on the master slave concept, this classification is made. So we say that it is the single layered drone swarm and the multi-layered drone swarm. Single layered means when all the drones are of the same configuration, all are at same level, everybody is informing everybody, then it is a single layered. Multi-layered, then when there are some slave drones and there's a master drone. So suppose these four drones are informing to this one master, and these four drones are informing to these one master, and these two master are informing to one super master or to the base, right? So this there may be hierarchy among the drones also. In that case, it is a multi-layered drone swarm, which is not actually our ultimate objective. We want to get rid of this, and we want to make the drone swarm which has the single layered, so that the self-healing can be achieved very efficiently. Of course, security is also compromised in case of multi-layered, because if this one master drone is killed, in case of defense usage, if this one master drone is killed, then these four drones will be killed by automatically. They will not be able to communicate with other members of the swarm, and therefore this multi-layered drone is, however, is relatively robust for the communication. Robust in communication, not in survival. In case of communication, they are robust, but in case of drone, in case of defense related applications or other long distance missions, multi-layered drones are not preferred. So this is the one classification. Another classification is based on the autonomy. The full autonomous system means from takeoff to land, everything is to be done by the drone swarm. Another is semi-autonomous, that the base through ADR or through some communication medium, the base, from the base, the operator is guiding the drone swarm that, okay, from this point to this point, if it is navigated, then after this point you go into this direction according to the feed from the drone swarm. You know, from one point to another point the drone swarm reached, and there is a feed, there is a input from the drone swarm of the situation to the base, and then the base is analyzing the information and then guiding the drone swarm. This is called the semi-autonomous system. But if after getting that feedback, the drone swarm itself is able to take the decision and to decide the further direction or further action, then it is a fully autonomous system. Of course, we are in process of the researchers are in the process of developing a fully autonomous drone swarm system. Okay. So what are the most important challenges in this case? From the algorithm development point of view, let me tell you, I'm not talking about from the hardware point of view. Of course, I'm not a hardware person. So I'm not, the challenges, those hardware challenges are aside. From the algorithm development point of view, I'm sharing the challenges. The one most important challenge that I feel, that the topology used for communication among drones. If you make this communication very strong, means fully connected structure, of course the communication is very, very strong and self-healing can be immediately achieved. But simultaneously, the drones, there will be a communication. A lot of computation is to be done on the onboard computer when a lot of communication is there. Because of this communication, a lot of computation to be done on the onboard computer, and you can understand that on the onboard computer the machine cannot be very heavy, and therefore the response may take delay. And if this delay is there, then there may be a collision. Because just imagine that if this is another challenge, that the one drone is here, another drone is here. Suppose the 10 meters distance is there, and usually for the long distance missions, these drones fly with around 14 meters per second. Around 14 meters per second is speed they fly. And just imagine if there is a delay in the response, between these two drones, even by 1 second, they will collide because there is a distance between them is 10 kilometers. Usually they keep around 10 kilometers, sorry, not 10 kilometers, it's 10 meters. 10 meters distance between them. This distance is also, this interagent distance is also again a challenge, that what should be the interagent distance so that the communication remain intact, and they can fly in the safe mode also. They should not collide with each other. So what should be the optimal interagent distance they should maintain always? What should be the minimum distance and what should be the maximum also? They can they go far, 20 meter far, or 25 or 30 meter or 100 meter far, so that the communication is not lost, and how close they can come so that the chances of collision are avoided. So this minimum interagent distance is again a challenge. Communication topology, that who will communicate to whom, this is again a challenge. So this minimum and maximum. Self-healing, I already told you that self-healing is again a challenge. How to handle if one or more drones crash, means who will take the place of the crashed drone. So this consensus is to be made, otherwise at one place so many drones are coming, then they can collide with each other. So all these consensus are to be made in the real time, almost real time, of course. And the next challenge is about the GPS denied environment. Of course, for the long distance missions, it is a GPS environment, but there may be certain situations where the GPS denied environment can appear in between. The enemy country can spoof the GPS blocking, and in that case, how to communicate with them, how to see their own location, that where I am, how to communicate the current coordinates to the base. All these are again challenges, that how to handle the GPS denied environment. Of course, these are the big challenges the researchers will solve over the time. So information, what I personally felt, that the less connected structure may be thought of. So there are many communication strategies possible. All those communication strategies are possible which are true for any swarm intelligence based algorithms. For example, the fully connected structure, ring topology, von Neumann topology, wheel topology, all those kind of topologies are possible for the drone swarm also. But I found that ring topology is relatively better when you actually implement them to the hardware. Okay, now I have already discussed these things. So let's come to the application areas where these drone swarms can be applied. So I've already shared that these drone swarms are very much applicable for the security, survey, monitoring, and surveillance purpose. And in fact, I personally feel that it is a future. For the border security also, the drone swarms are being developed where the drone swarms are working 24 hours, means they are powered by the poles, by a thin wire. They will be powered by a poles, and they will be in the sky throughout the time and in a certain area, and they will be communicating with each other. So even if there is any disturbance at one place, it will be communicated throughout the border, and without actual men on the border, the security or surveillance can be made. Disaster management is the one most important, and the government of India is also working for this purpose. If there is any disaster, UAVs can be sent and can do the surveillance, and immediate relief can be dropped. So this is the problem. Actually, I worked on this project, and this is the problem, that if there is a flood kind of situation is there, and some humans are trapped in certain area or something, then the drones can search the humans. So the system is trained with the computer vision. It is trained to identify the humans, and once a human is identified, then the medicine or some kind of inflatable boat or something, any relief material, whatever is the relief material, is dropped to that human being nearby. Within 10 meters, distance it can be dropped. So these kind of applications are there. And let me tell you, it is very successful also. This is a practical, this is reality now. Search and rescue, I think you may have heard about that General Rawat, the Chief of Defense of India, killed in the, died in the air helicopter crash. And at that time, to search the black box of that helicopter, the agencies took around 10-12 hours. So this can be done very efficiently with the help of drone swarm. If the suppose 100 drones are flying in certain area, suppose 10 by 10 kilometer area, they can search much better way than the humans search in that particular area. They can fly very low, 30 meters height, they can fly very easily. So the future is actually very bright. Let me tell you, by the time you understand that the drone swarm future is very bright, the autonomous vehicles, for the development of the autonomous vehicles, the drone swarm are important. Yeah, one more thing I want to share, that the similar kind of technology can also be used for the autonomous cars, self-driving cars. When so many cars, self-driving cars are there on the highway, then how they can communicate with each other and how they can take the benefit of the presence of others. What I want to say, that if one car is ahead and there is suppose some hurdle or some obstacle there, it is taking sharp brake. So this information can be immediately shared with among, suppose 1 by 1 kilometer area, immediately this information can be shared, and other cars can get alert that at that particular place there is some obstacle, so let's slow down the car. So this similar kind of concept can also be implemented with the self-driving cars. The parcel delivery system, the defense, the search and rescue mission has ultimate applications of the drone swarm. The major challenge in the drone swarm is the development of the algorithm and of course the hardware related problems. Right now in edge compared to the hardware, I'm not much aware on that, but while working on the project, I realized that the powering the drones for the long endurance is the major problem. The battery system, if you want to the flight time, more than 1 hour flight time, you need to put a large battery, and that carries a lot of weight, and of course if the weight is more, the endurance will be low. If you are putting some engine, means fuel based drones you are making, then there is a lot of sound, and if the sound is more, oral signature is very high, and in that case those kind of drones may not be used for the defense purpose. If the oral signature is very high, the enemy will be immediately alerted. So these kind of challenges are there. Future is there, but future is very bright, and definitely one day we will have the good technology for the power also to power the drones. This is the one problem that right now we are solving: drone flocking optimization using NSGA2 and the PCA. We have applied NSGA2 and PCA for this drone flocking optimization problem. It is done with a collaborative project with the Liverpool Hope University and my university, South Asian University. Myself, my research associate, Mr. Nikhil, and Anicho is an assistant professor in Liverpool Hope University, and Professor Atul Nagar. We 4 people are working in this project. So I just want to share our findings quickly. Our findings. I know the time is running out. So just quickly, I share what we have done. First, we have developed a flocking optimization problem. The drones are flocking. So this flocking optimization problem has 12 decision variables, 12 parameters, and 6 objectives. We formulated these 6 objectives and 12 decision variables. We developed a Python simulator MOFlock, multi-objective flock. We named it as multi-objective flock. And using the PCA, principal component analysis, we reduced these 6 objectives to be the 2 objectives. And we also use this PCA to understand the collective dynamics of the multi-agent system. And then these 2 multi-objective optimization problem is solved using NSGA2, and a Pareto frontage obtained. now this is the first time we have done this. This is best to the best of our knowledge. This is the first time